Our next presenter is Anthony Smith, who traveled far from UBC and is talking about mapping the population at Ecumene of British Columbia with Dasymetric GIS methodology.
Good morning, everyone. Before I start, I want to say if there's two things you take from this, hopefully it's that you understand the two words there, Ecumene, which comes from the Greek word I'll explain, and Dasymetric, which is basically the approach to improving cartographic representation that I'm going to present today. I'd also just like to acknowledge my supervisor, Brian Klinkenberg. This was an undergraduate honors thesis project that I worked on over the summer, over the 2 summers ago, and then have since refined. And I'd also like to thank the Human Early Learning Partnership. It's a research group at UBC that has employed me for the last 3 years doing cartography and spatial analysis. So, without further ado, here's a quick overview of this sort of agenda for today. First, a quick history lesson, review of some of the relevant literature in this field, and then I'm going to look at each of the data sets that I'm using. I'm going to integrate 9 different data layers to produce a map of where people live in British Columbia. And it involves kind of a new binary multi-level approach, which I'll explain. I'll look at 2 different applications, one for cartography and one for analysis, kind of tying into the representation and themes of this workshop. And then I'll look at limitations and some future applications. So, history. I'm sure that the term antipodes is in people's kind of back of their minds, but this is Créte's early rendition of the known Earth, according to the Greco-Roman era. So, oikumene, as it was spelled in that time, basically meant all the known lands, all the areas of the Earth that the Greeks knew about. And the modern translation of that word into ecumene essentially means inhabited lands, or places where people live. It also has other applications in terms of agricultural ecumenes or industrial ecumenes, but I'm looking today at population, which is just where people live. It also has a long history. This is an example of Jefferson's map from 1934. Shows basically the black is the population distribution of Canada as he imagined it at that time. It wasn't a very sophisticated method. He just basically drew his best guess. A little later, Gadja in 1960 took a more sophisticated approach and based his layer on sort of transportation networks. At that time, it was a lot to do with railways. But again, it's very coarse-grained, it's not sophisticated, it's hand-drawn. A later version by Hamlin in 1972. I only put this because I love the last category up there, the unattractive or repulsive areas of Canada. Obviously, his language was not very technical. But most recently, Statistics Canada has produced a Ecumene, as they call it, which is freely available on their website. And it's designed for a national scale. So it's basically a 5-kilometer or so buffer around big cities and major population centers. So it gives you a good picture of the kind of distribution. If you focus on British Columbia, see the pathway at the center, the interior, and some other pockets outside that central axis, and then the lower mainland on the left side. But the big drawback to this is if you zoom in on Vancouver, it's this giant blob. There's no local resolution. So what the goal of this project is to zoom in and get a more a fine-grained analysis. There have been other global attempts to do similar projects to mine. This is the Landscan data set. This is Houston, Texas, and one of the beautiful features of this data set is it's got daytime and nighttime populations. So for disaster evacuation, it's a great data set to know where people live or where they are during the day. The problem with this is it's private and very secretive. There's not a lot of methods published on it. You can't replicate it. So for me, I can't create this for Canada, and I can't afford to buy it. The other global data set is the global population, or gridded population of the world. It's up to version 3 now. But it's, again, a 1-kilometer grid cell. So this is the data for Vancouver I downloaded and classified myself. And that square of red is Vancouver, but it's not going to help you at a local scale. So then let's look to the literature and see what's been done at a more local resolution. Throughout the thesis, the first part of the thesis is actually a 20-page literature review. So this is just a summary of a few of the papers. The most famous Dasymetric mapping study is J.K. Wright's Cape Cod example. Basically, he took some census data, and instead of mapping it across the whole census unit, he interpolated the data to be represented only where people live, and therefore improved the communication of the data. More recently, Holloway et al. Has done a lot of work using land cover data to also refine display of population data to where it's more meaningful. And I'll just leave this, if you want to look up my paper and the proceedings, there's some resources for you. But to focus on the Holloway paper, there's a significant drawback to her study, and that is, at the end of the day, the population is distributed into these four categories of land use in ratios. So 80% of the population from a census block. If you take a block, if there's an area of urban, basically she takes 80% of the population and puts it in the urban box. And she spreads it around. Thank you. So it's a population distribution. It's not a binary cut of where people live and where they don't. It's a way to basically population map. The goal of my study is not to do this kind of distribution of ratios, it's to draw a line in the sand. So to do that, I've employed, basically throughout my work, I collected every data set I could possibly use, and through that literature review, I looked at what's been used in the past, and I tried to find the best data to meet what's been done in the past, and also came up with some new versions. So the baseline, where people live, census blocks from StatsCan. Blocks are basically every road intersection. They're quite small. The big drawback to a block, though, is the population is assumed to be heterogeneously dispersed across the block. And up north of BC, there's blocks that are several hundred square kilometers, several thousands even. And the people might all live on one small corner. But you can't calculate the density more accurately than the whole block. So what most people, including the Holloway study, basically take land use data and chop off the unpopulated areas and redistribute the population to that corner. The big drawback in BC is this baseline thematic data is only accurate to about 250 meters, and in areas of high spatial relief, the accuracy is up to 1 kilometer off. You literally have a town completely in the wrong place. So it's not very reliable. There is a more accurate land cover data set that the government of BC has worked on, but there's some major classification errors in the data as it is. So I could only use one category from it, and that's the built-up area, which I use to show areas that are possibly populated. To move on, I can also show where people live based on urban land use. That's only available for urban areas. There's about 6 different areas in BC that we can get that high-resolution zoning data. Things like residential, institutional, commercial, etc. I also can say people don't live in parks. That's federal rules. People live generally somewhere you can drive to. And they also are more likely to live in places where there's high density of road networks. So I did some calculations to create basically a density measure of roads. So if there's a lot of streets intersecting, there's a high probability someone lives there. I also, for the first time, integrated local delivery units or postal code polygons. And I said that anywhere there's no postal delivery, there's not likely a permanent address there, because the postal system covers everyone. And lastly, or second last, the digital elevation model was used in 2 ways. First, I looked at BC and I said, there's no one living above 1,200 meters. That's basically glacier world. And secondly, I used it to calculate slope. In the Holloway paper, I replicated her method and said anywhere with a slope greater than 15 degrees is not likely to be built upon. Lastly, people don't live in water, although they do live in houseboats, and I bring that up later. So, to move on, I think I'm about halfway through, so hope I haven't lost you yet. This is a very broad sketch of the whole process, and I'm going to walk you through this step by step later, so I just want to highlight the basic structure of this. It starts up here with population density greater than 0.4, and that's areas where there's a high likelihood people live in that census block. And you take those census blocks and you essentially erase the areas that are land use categories that are not inhabitable. So alpine areas, barren forest, wetlands, young forest. According to the satellite data, people shouldn't live there. And you take the result of that, basically you do an erase function. You take the result of that and you add back, and here's the multi-level part, you add back areas that with higher resolution data you're very confident people live there. So areas that are urban and residential mix, built up areas, residential, commercial areas, and road densities with high line density. So you've taken what you start with, erased something, added something back, and then lastly you take all these areas that you're very confident no one lives in, and you erase those from the sum of the first part. So let me show you that in map form. Start with areas that have census population greater than 0.4 or 1 person per square mile. It's a very standard population baseline. You erase from that all the land use categories that have very low probability of being populated. At this point, you've actually cut away too much. There's entire communities up here on the Haida Gwaii Islands and several small communities along the interior that are actually completely missing at this point. So if you stop now, you'd be missing towns. Because that data set's only 250 meters resolution, it's actually missing quite a bit. So then you add back all the layers that you're very confident people live here. It's the line density, the urban residential areas, and so forth. And from this, then you clip away all the areas you're very confident there's no population. So 0 population census blocks, postal delivery units with no population, areas further than 1 kilometer from any road, or elevation greater than 1,200 meters, etc. So this is essentially the final result. You can see in black the sparse dispersal of population. This represents about 2% of the land area of British Columbia, and if you just take the population that falls within these areas, according to census blocks, that's 98% of the population. So you can pretty much say that's where people live. However, for visualization, it's important to improve the cartographic representation of this for various scales of mapping. And a lot of the mapping I do at my job is regional or provincial. So what I do here is basically you take the Ecumene area, this is the central interior of BC, and you add some circular buffers simply to improve the cartographic representation. There's no technical reason for using a kilometer buffer, except that at this scale, you can see it. And I'll explain more about that later. Finally, the result at a provincial scale is the red Ecumene area, or inhabited lands, and then some sequential buffers to help you see what you're looking at. And you can see there's this large area up here in the Peace region. This is flatter agricultural land, so population's actually quite sparse, but it's still populated. And Prince George, Kelowna, and then this sort of spine up the Georgia Strait, and then lots of small communities up north. So that's the poster. Next, we did do quite a bit of community consultation. My project is actually about collaborating with communities, and we put all the data into Google Earth, and that's the yellow. We also produced kind of a smoother, simpler version, that's the purple, and we sent it out to our contacts all across 59 different school districts. We've sent it out several times, and basically everyone said, yeah, that's our community. It looks right. You can see kind of transparency that, you know, it's caught just about everything. There's this industrial area up here that there's nobody living in it, so if you just use satellite land use classification alone, that would be an urban area, but it's not populated. And similarly, it's caught the parks and some of these institutional areas with zero population. So the Google Earth is actually really helpful because it did identify some of the limitations that I'll talk about later. So I'd like to focus on two applications. First, cartographic side, and this was the real driver behind this project in the first place. I'm sure most of you are familiar with the choropleth map. It basically implies that the data is spread evenly across each polygon. So this is just, ignore the data, it's just an imaginary map of, in this case, school districts, neighborhoods up north. And big red area immediately draws your attention to it and could very easily draw policy attention to it, or it confuses the message a little. When you hide the unpopulated areas, you get a much more accurate picture of what's going on. So you can see the population spread pretty much along the highways. You can see the extent of Vanderhoof more accurately and very low population up here. So this is the main purpose behind this layer. It's a cartographic technique. And it's very easy to apply because all you do is put a GIS layer on top and hide the data below. To be a little bit more sophisticated, you can also do some spatial reanalysis or spatial interpolation of the data and actually create some new underlying data. So here's a choropleth population density map of Vancouver. You can see the zero population. These are census blocks. There's a few areas that are clearly identified as zero population, but one would assume that since the mountains start here, there's very few people living in these areas. So what you can do is reproportion the data within the Ecumene area. This is the non-buffered area. This is just as it comes out of the data. And you get a much better picture of where people are living. You can clearly see the terminal area. This is train tracks just south of Vancouver. You see land, the forest area around UBC. The airport, nobody lives there, but there is a small community on the edge. And up on the mountains, there's no one there. So this is probably the more sophisticated use of this layer, and it's very easy to apply again. You literally erase the unpopulated area, and you're left with the result. Now, of course, there are some significant limitations to this. It was an undergraduate project, after all. It's relying on data that was sometimes up to 10 years out of date. Census data is 5 years out of date. Olympic Village wasn't built 5 years ago, so the whole False Creek area is not populated. It's also missing temporary cottages, boats, even Granville Island in Vancouver. There's a whole series of boats there, but they're not captured in this because they're not actually on land. Additionally, using the 77-meter DEM for slope calculations along the North Shore Mountains proved to be about 100 meters off sometimes in the line where houses were, especially on the North Shore where houses are built on very steep slopes. And lastly, or second last, the data itself, I had to spend a year figuring out all this data. It's something I use every day, so I understand that elevation in BC is 1,200 meters is a meaningful number. And similarly, the road density, I was using the line density tool in ArcGIS. And I had to experiment with the settings and overlay it on Google Earth to see what the best settings were to approximate what community, what was a meaningful density. And I picked a number and stuck with it, so it could be replicated now. Lastly, the process itself, if I did it once and then I actually replicated it again a second time, and it took about 5 days to process. Half of that's just organizing the data, clipping it to BC's land area, reprojecting it, and the second part, the actual erase functions and the addition functions, is about 2 days, an hour to 5 hours processing. So in the future, I'd love to just use more automated Python programming to just do this all in one go. Or you could even use the visual layouts and what's it called? The art tool that you can make little boxes. Art objects. And lastly, I put this in after Sat's comment, the circular buffers are really just there for visualization. I would love to have some more sophisticated way of expanding this so you could actually see it at a provincial scale. And that ties into some of the next steps if someone wants to take this on. I don't think this will be my next master's degree, but there's certainly areas to look at. Calculate Ecumene for Canada or the world. You could do this easily for Canada. Most of these data sets are standardized across the country at least. Also, there's a new tool in ARC 10 called the fuzzy overlay tool, which allows you to take layers and assign probabilities to them and basically say, I could do all this calculation instead of erasing, I could do some kind of weighted addition subtraction algorithm and also say something like people are more likely to live next to water and therefore add a spatial tolerance to that. Lastly, there's lots of more exciting data out there. Cadastral data, there is a land registry for BC, but you have to be high up in government to get access to it. There's obviously new techniques for classifying land use data, and LiDAR represents the ultimate in this kind of analysis for land use classification, but the data sets are enormous, especially at a provincial scale. And last but not least, I would love to do a more sophisticated website where communities could log in, manually move the layers, improve this based on actual observation or local knowledge. And that kind of a feedback process would be really useful to improve the end result. So in sum, it's, jumping ahead there, it's a new approach. It's very straightforward and easy to replicate. The beauty of doing the multi-level step is that you can use all your data, but you take what you know and then you improve it with the second pass. You can use the regional level data and the local level data. And the end result, using a binary approach, allows you to create simple overlay masks that you don't have to do any recalculation to use. You just drop it on top of your population level data set and you can basically produce your maps as is. Or if you want to erase the empty space and recalculate your densities, you can also do that. So thank you very much for your attention and look forward to questions.